Hi, good morning friends. Today we are back with this reaction dynamics, the concluding part of reaction dynamics, that some of the, as I mentioned in the last lecture, that maybe little portions which are yet to be talked about. So today that I will cover. Of course, I will give some introduction to that, and then I will switch on to a topic which we did not talked about, is basic very basic idea of corrosion. I mean, rate processes related to corrosion, how to measure rate of corrosion, a preliminary idea of that. Okay, now so far as reactive scattering is concerned, now quantum scattering theory is very useful in dealing with the potential energy surfaces. Now simple reactions like A plus BC giving rise to AB plus C. So here this now this dynamics of this chemical reaction is very much dependent on the topology of the Born-Oppenheimer potential energy surface. Born-Oppenheimer potential energy surface. This is Born-Oppenheimer. Born-Oppenheimer potential energy surface. Now this in quantum mechanics, total wave function is it has got this electronic part, vibrational part, rotational part, and nuclear part. So if you think of electronic motion, then electronic motion motion is very fast compared to vibration, and vibration is even faster compared to rotation. So the point is that if you think that like as they are separated in time scale, now কিছু প্রবলেম আছে? তাহলে আবার শুরু। Okay, so Born-Oppenheimer potential energy. So basically electronic, vibrational, rotational, and these motions. So as they are widely separated in time scale, therefore total wave function psi can be written as the product of individual contribution, that is psi electronic, psi vibration, psi rotation. So you can write in this way. So based on this you can I mean this is the total wave function, electronic, vibration, rotation, and maybe you can include the nuclear part as well. So the thing is that based on that you can generate the potential energy surface, that is which is dependent on the Born-Oppenheimer approximation, and the dynamics of this chemical process is very much dependent on the potential topology of the Born-Oppenheimer potential energy surface. Now even without the exact calculation, quantitative idea on the chemical dynamics can be gained from the inspecting the properties of the potential energy surface. Okay, now here you see that this is A plus BC giving rise to AB plus C. So this is, as I told in the last lecture, that this is RBC, that is distance between B and C, and RAB, it is the distance between A and B. Okay, and this is your this is the cross section, potential energy, equal energy line, contour for the corresponding equal energy line. So this is the minimum energy path. Okay, so giving rise to the product AB plus C. okay, this arrow, and this is the highest energy point, which is called the transition state, okay, and reaction profile for a linear approach of the 3 reactions. So, in this case it is a linear approach, A approaching this way, it is approaching, okay, it is a linear approach, and the path of minimum energy from the reactant to the product of the potential energy is termed as the reaction path or the reaction coordinate. So, this is your reaction coordinate, okay, this is your reaction coordinate, and this corresponds to dE, I mean electronic dissociation energy for BC, and this corresponds to the electronic dissociation energy for AB, dE. Anyway, so and the energy barrier, that is the saddle point, this energy barrier separating the reactant and product values is termed as the transition state. So, this is basically, you know, when we draw in normal case, that we draw like this, okay. So, this is your transition state, this is your reactant side, this is your product side, okay. So, this is separating these two you know values, okay. So, you can do this thing on the basis of this, I mean on the basis of the applicability of Born-Oppenheimer approximation, that motion, I mean motion of electron, motion of electrons are much faster compared to vibration, and that is much faster compared to rotation. So, therefore, they can be separated as the product, and therefore, accordingly your solution to Schrodinger equation becomes easier than when they are mixed together, these you know electronic vibration, rotational motions, I mean these coordinates are I mean mixed together. Anyway, so and if the total energy of the reactant, that is the sum of the collisional energy, then I mean sum of the collisional energy, that is EC, termed as EC, then vibrational energy EV, and the rotational energy ER, and of course the electronic energy, if there is an electronic energy available, that is higher than the barrier height, okay. So, if you add them, all of them, rotation, vibration, then collision energy, of course if there is any electronic, you can add that. So, if it is higher than the barrier height, the reaction can proceed in principle. So, that means it is above, so energy is above than the barrier height. So, your reaction can proceed, okay. So, the available energy AVL after collision is distributed among the products. So, this amount of energy is distributed among the products. So, this is your initial, this is your final, okay. So, this is the reactant side, this is the product side, okay. So, this means if this sum is more than your this height, then the reaction can proceed in principle, but if it is less, then you know in principle the reaction may not be possible, okay. Now, again think of this line of approach, I mean say this is A, this is B, C, you join them with line, and then what you do, that you know draw another diagram where B, C is there, but A is approaching at some angle, okay. So, maybe that angle is gamma. So, in that respect what happens, that your reaction may be less facile, or maybe in some cases, if that is the optimal angle, then reaction may proceed in a better extent. So, the point is that this barrier height may be dependent on this angle of approach, okay. So, in that case, for an A plus BC reaction, the barrier height is in general and in changes, barrier height general changes for different approach angles, and if more energy is stored in the reactant, the barrier can also be crossed for approach angles differing from the optimal value, okay. And there is a cone of acceptance of the reaction, I mean that can be increased. Means if the energy stored in the reactant is more, then maybe other angles are possibly acceptable, okay. So, suppose if this is your optimal, say this is your optimal angle, gamma, say gamma is equal to 180 degree, then in another case if gamma is less than 180 degree, in that case what is happening, that maybe you need more energy to overcome this barrier, that is barrier is more. So if you plot, if you plot basically this probability, okay, I mean barrier height in terms of various angle, then you will be seeing that for this particular reaction, okay, so barrier height may be increasing, okay, barrier height is still higher for other angle, very high barrier, okay. So maybe this is the lower one is 180, then maybe 150, then 120, then maybe another maybe 90 degree, which may be even more, 90, and the other one is maybe 60 degree. Okay, so this is barrier height, and this is your progress of reaction. Progress of reaction. So therefore, angular approach, I mean angle of approach is an important factor. So if you change the angle from the optimal value, then barrier height accordingly gets altered. Okay. So therefore this, and of course if your energy, I mean energy stored in the reactant is more, then cone of acceptance for the reaction may be increased. I mean you have got your like B, C, and say optimal angle is say 180 degree, maybe your reactant can approach this way. Okay, so this is your cone of acceptance. So if this cone of acceptance may change. Okay, cone of acceptance may change. So that means here more energy is required to overcome the barrier, and barrier height is also more. In this way, this is another cone of acceptance. It is cone of acceptance is more. So thus cone of acceptance of the reaction can be increased, and if the energy stored in the reactants is more, then the barrier can also be crossed for approach angles differing from optimal value. Okay, so optimal value is 180 degrees, so that can be overcome. Okay, so and this is your this is the potential energy profile. I mean whatever I have shown over here and is shown over here is the potential energy profile along the reactant coordinate for this reaction. I mean this is this example is given for the reaction H plus H2. It's the potential energy curve H plus H2 giving rise to H2 plus H. Okay, so and this is the potential energy profile along the reaction coordinate, for different values of this approach angle. Okay, say this is your hydrogen, and say this is your dihydrogen. So this is the this is gamma. So H, this is H, another H. So H1, H2, H3, 1, this is 2, 3. Okay, next effect of vibrational and energy and kinetic energy. So I already have given you a little idea in the last lecture, and which is known as the Polanyi's rule. Okay, Polanyi's rule. So, we will just give you a little idea. Now, for symmetric reaction, okay, when the reaction is symmetric, then your potential energy, I mean the transition state, okay, transition state is symmetrically distributed. I mean, look at it. This is the contour, okay, and see, this is your minimum energy path, okay. This is your transition state for the symmetric reaction, okay. So, this is 1 r, this is r primed, okay. Now, what happens that if your transition state is resembling your more product like or more reactant like, then what is going to happen? So, for that is why the effect of vibrational and kinetic energy is more important. So, effect of vibrational energy and kinetic energy is very important, okay. Now, for asymmetric reaction or the reaction which is not symmetric, the transition state usually located. So, the case is, if it is not symmetric reaction, so your transition state is symmetrically distributed in the reactant side and product side. But if it is not symmetrically distributed, then what will happen? Either this will come close to this side or maybe it will go to this side, okay. So, for asymmetric reaction, the transition state is usually located closer either to reactant or product side. If it is close to reactant side, so asymmetric reactions, the transition state located, which is located closer to or nearer to reactant or product, okay. If it is nearer to reactant, it is called the early barrier or early transition state, early barrier, that is barrier is closer to your reactant side, or maybe if it is product side, it is called the late barrier, okay. Now, if we then inspect, that is, if we inspect carefully the favorable reaction trajectories, it can be said that for an early barrier, if it is an early barrier like this, see, this barrier is early, okay. This is the early barrier case, okay, and this is the case that is the reaction will proceed, and this is the case that no reaction will hindrance of reaction, okay. Reaction does not take place, that is the arrow is not, the path is not like this, as it is not, it is shown that the path is basically coming back to its reactants, you see. So, what is the situation for an early barrier? Translational excitation, okay, that is having higher kinetic energy, translational excitation of reactant promotes the reaction, that is, if it is higher translational energy, you see that it promotes, that is, it allows crossing this barrier and leads to vibrationally excited, okay. This represents vibrationally excited, you see. Vibrationally excited means it is following this maybe it is not following lowest energy, but the path which it is following, it has got higher energy, and that must be vibrationally excited product, okay. And what happens that vibrational excitation, if it is vibrationally excited, then what happens, it is going this like this. So it cannot cross this. Okay, going like this, and after some time it cannot cross the barrier, but it remains in this you know, valley. It cannot cross this cross line or this saddle point. So reaction does not occur. So vibrational excitation hinders the chemical reaction, okay, for an early barrier. Okay, so you see that is H2 plus F giving rise to HF plus H. Okay, so early barrier corresponds to you know, vibrational excitation corresponds to hindrance of reaction, but translational excitation corresponds to the product with vibrationally excited situation. Okay. Next, when the case is, it is the case of Lett barrier. Okay, when it is the case of Lett barrier, I mean barrier is here, it is nearer to product side. Okay, it is nearer to product side. So what is happening, that you see this is your initial side, this is your final side. So for a Lett barrier, vibrational excitation promotes the reaction and leads to products with high kinetic energy. Okay, so vibrational excitation, okay, it will lead to, you know, vibrationally excited state. So this will ultimately help, you know, in crossing this barrier, and then it will move to the product side. But since it is vibrationally excited, so excess energy will be transferred to the product in the form of the kinetic energy. But what happens when it is the translational excitation? When it is translational excitation, you know, it is reflected back. Okay, so so it is reflected back to, you know, here. So therefore for Lett barrier, okay, that is for Lett barrier or later transition state. Okay, what is happening, that that vibrational excitation promotes the reaction and leads to product with high kinetic energy, and translation excitation of reactant hinders the reaction. So these are the two opposing situation. Okay, when it is Lett barrier and when it is early barrier. I mean the same reaction has been represented in opposed way. In this case we are considering the backward reaction to be like this, and in this case we are considering the forward reaction to be like this. So for the backward reaction it is early barrier and the forward reaction is the Lett barrier, but the situation is different. So that is the effect of vibrational and vibrational excitation, and also the kinetic, I mean translational excitation. Okay, so that's you know, about this Polanyi's rule. Now next, so that will conclude more or less the chapter of you know, this reaction dynamics. There are other aspects also, endless things are there, but because of you know, the scope, we should stop over here, and the topic that which I am now going to cover is different from your this dynamics, I mean reaction dynamics, that is your corrosion. Okay, so corrosion is a thing that we have not dealt with earlier, but this part I guess I should talk, at least you know, I should give you a little idea of these things, that this is basically an electrochemical process. Corrosion is an electrochemical process. Corrosion is an electrochemical process. Electrochemical process. Okay. And how this corrosion can be controlled, and what are the factors that are responsible for corrosion to occur. So, factors important here, and how to control, and how to measure corrosion rate. Okay. Now, let us start from metal dissolution. Metal dissolution. What is metal dissolution? When a metal is dipped into a solution, then what is happening, that metal loses electron. So, M goes to M n plus n electron. Okay. So, now in most of the corrosion processes, excepting cathodically controlled processes, metal will dissolve. Okay. Because corrosion is mostly related to metals. So, metals will dissolve, and we should have an understanding of the principle behind the metal dissolution process. Okay. And that will be an important part for understanding corrosion. Okay. So, in this case, consider a piece of pure metal M in a solution which contains its own ion, say like copper, which is dipped into copper sulphate. Okay. So, copper sulphate means Cu Cu2 plus, Cu, and here it is dipped Cu2 plus. Okay. So, in this case the metal has solubility in the solution in which it is placed, and copper in copper sulphate. So, general equilibrium reaction is like this. This is the general equilibrium reaction, and at equilibrium there is no net current. So, equilibrium, no net current flowing. Okay. So, in one case no net current flowing. So, in one case the reaction is like M to Mn plus Ne minus, and the reverse process. Okay. So, reverse process is that, because and the reverse process is like M n plus Ne giving rise to M. Okay. So, there is no net current. So, electrons produced in the reaction above, I mean here, okay, it is combined with the metal n plus to give you M. Okay. And that is deposited onto the metal surface. Okay. So, this way situation occurs. I mean this may be the two processes that could happen. So, I mean in one case it is dissolution, in other case it is deposition. Okay. So, basically if you have another copper over here, so this reaction will take place, I mean the second reaction will take place. So, these are the half cell reaction, half reactions. Okay. So, these are half cells, okay, or half cell reactions. Okay. So, these individual reactions are called half cell reaction, as they produce electron. One of them will produce electron and the other will consume it. Okay. So, oxidation actually produces electron. So, this is oxidation, it produces electron, and the reduction is the consumption of the electron. Okay. And both this oxidation and reduction reactions. So, half cells means redox reactions. So, both these reactions, that is oxidation, reduction, oxidation, reduction, these are very important, you know, in corrosion. Okay. Now, what is happening that suppose like as I mentioned that, you know, when metal dissolves, say copper sulphate, this is Cu, this is Cu. So, copper dissolves, and if there is nothing happening, then I mean that electron is again collected by copper 2 plus to deposit over here. Okay. But one thing is what is happening, that half cell reaction, if this half cell reaction, you know, if they do not involve the same element, so then what is happening, the electrons produced in that is produced in, say, in this reaction, suppose this is copper and this is another element, say M, and what is happening that if this electron produced in the forward reaction, that is say dissolution process, is not available for the back reaction, okay, then that will you know, the electron which is generated over here will replace the other ions back to the metal state, I mean like M to Mn plus N electron. So, this electron is used up for reducing another Mn plus Ne to M. So, if that does not happen, okay, that is instead electrons from oxidation reaction are consumed by a different reaction, resulting a new reaction product. Okay. This leads to secondary reaction between products of oxidation and reduction half cells to form stable material. So, if that does not happen, but secondary reactions are taking place giving rise to stable products, then what is happening, this can further react with environment to form stable compounds such as rust. Okay. And these are then very difficult you know, to get back to its original case, that is original metal. Okay. So, that means because of this secondary reactions, you know, this whatever products are generated react further to produce something like rust, and rust is, you know, it is very difficult to get back to you know, iron. Okay. And that is basically the corrosion process. So, basic corrosion process. Basic corrosion process, it is, you know, first one is oxidation. Half cell reaction, oxidation half cell reaction. So, this is basically your metal to metal N plus N electron. Okay. So, this N electron, you know, if it is you know, if this if there is no, you know, current flowing, what is happening at equilibrium, again, you know, it will go back over here to get back your metal. But if that, you know, suppose this is stopped, so say this is not there, or maybe this is further, I mean this is further used up in other modes, then this equilibrium is shifted towards the right. So, when there is no net current flowing, then equilibrium is expected to be established. Okay. But if there is a net current, that is if this is taken up by something, then you know, cathodic process, like this is in the, you know, anodic process. So, you know, if it is cathodic process, think of a cathodic process where this electron is used up. So, reduction half cell, other second step is your reduction half cell. reduction half cell reaction. Okay. So, cathodic maybe secondary process, cathodic processes like say M primed N plus N electron giving rise to M primed metal. Okay, this could be one process. Another process could be like if these electrons are used up in other reaction, like say converting H plus proton to half H2. Okay, so this plus electron giving rise to half H2. So this could be one reaction. Another is maybe another possibility is O2 in presence of H plus 4H plus 4 electron giving rise to 2H2. Okay, you see that these are used up. So equilibrium is now shifting this way. Okay, maybe say Cu2 plus electron giving rise to Cu plus, that is one state. Okay, maybe O2 plus H2O plus 4 electron, 4 H2O plus 2 H2O plus 4 electron. Okay, let me write it again. O2 plus 2 H2O plus 4 electron giving rise to 4 OH minus. Okay, so these are the reactions that may happen as the second step. Okay, as the second step. So for many practical situations, these reactions, I mean this particular reaction, okay, is very important. In this case, oxygen present in the water will dissolve and giving rise to alkali. Okay, so so that is the giving rise to OH minus, that is alkali, and this is a slow dissolution process. So this is your second step. Now third step, or rather a part of this may be regarded as the part of the redox, so both half cell reactions. So okay, next will be, third one is your cathode side. Okay, so important feature is that we have to distinguish between the cathodic half cell reaction. So we have to distinguish between cathodic half cell reaction and what is meant physically by cathode and the physical cathode. Okay. Now this physical cathode is a localized region, is a location where the cathode half cell reaction occurs. So here in this physical cathode, here cathode half cell reaction takes place. Okay, here cathode half cell reaction takes place, and cathode only provides, now this cathode, this physical cathode, this provides, what does it provide? Provides the electrical conductivity necessary for electron transfer for cathode half cell reaction. So it provides electrical conductivity, electrical conductivity which is necessary for electron transfer to occur at the cathode. Okay, and this reaction will occur on a surface which has the capability to conduct electrons. So surface is very important. So provides electrical conductivity, and the surface and its surface is very important. So it should have the capability to conduct. So conducting surface. conducting surface. And in some cases what is happening that some other non-metallic materials maybe which is conducting can act as the cathode as well. Okay, electrically conductive materials can be cathode, and it should also be apparent that the cathode does not in that case dissolve and can be termed as being cathodically protected. I mean it is a protected one which does not dissolve. Okay. Another cathode reaction is the reduction of hydrogen ions, as I told you, and in this case hydrogen gas will be nucleated over there at the cathode. So, for this half H2 which is generated from H plus electron. Okay. So, reduction of H plus. So, this as a result of this hydrogen will be will be covering the cathode surface. Okay. So, and nucleated, and this hydrogen will be nucleated, and this distinction between cathode reaction and cathode material is important when we look into the localized corrosion. Okay. Localized corrosion means the corrosion when the corrosion is very much localized in nature. Okay. Basically it may be thought that the regions which are not corroded are maybe cathodically protected. Next is the fourth one is your ion transport. Ion transport. Now, this process where ionic transport is very important. So, if the medium like if electrolyte is present, okay. So, if the medium is conductive, that is containing electrolytes, it is very important. So, the presence of electrolytes is of immense importance. In many cases environmental exposure for environmental exposure I mean when exposure of your material in environment like water, through water, maybe sea water, maybe acidic water, or maybe alkaline water or alkaline medium is very important. The greater the ionic flow capability of the solution, the greater is the corrosion rate. So, that means conducting property of your solution when it is high, then rate of corrosion is also high. So, that means the greater the ionic flow capability, the more is ionic flow capability, more is corrosion. Okay. Thus, and another important point, if you use distilled water with high resistance and low conductivity, usually in this case, if you replace this, now if you replace all this wherever needed with distilled water, replace with distilled water, then the corrosion rate is low. Okay. So, in this case corrosion rate, because compared to your sea water or acidic water, alkaline medium, this has got low conductivity. So, low conductivity means it does not support high corrosion. Okay. So, ion transport is very important. So, that means ion transport. So, ion transport rate is important in determining the corrosion rate. Okay. Next is electron transport. electron transport. So, there must be a mechanism by which the electron will be transported between the cathode side and anode side. So, electron transport between cathode and anode sides. Okay. Now, since electrons are produced by oxidation in anodic half cell reactions, okay, electrons are produced half cell reactions and consumed by the cathodic reaction. Okay. So, it is produced and here it is consumed. Okay. So, that means electrons will flow from here to here. Okay. So, without flow of electrons between anode and cathode, these half cell reactions will not be completed. So, that means there must be some means like electrical, I mean wire connection, okay, or wire connection, I mean electrons flow along wire from anode to cathode could be a way. So, if by some means we can hinder this electron flow from one side to the another, then possibly we can reduce the extent of corrosion. Okay. So, if we can impair, I mean if we can stop it, then maybe corrosion can be reduced. So, therefore these points are to be looked into, giving importance. Okay. So, now the thing is that this, in summary, what you can say that these 5 points I mentioned, those 5, 1, 2, 3, 4, 5 points I mentioned, that these are the necessary processes that are necessary for corrosion to occur. I mean wherever this happens, corrosion is there. Okay. So, that means these are necessary. So, that means your like half cell reactions, then cathode side, ion transport, electron transport, these are important points. So, cathode and anode reaction, electrolyte, then electron transport. These are the very important points. Okay. As for example, many materials like steel, if we put steel in water, okay, and what is happening that all these processes, as I mentioned, I mean half cell reaction, transport, ion transport, electron transport, all these happen. Therefore, steel in water will undergo corrosion. Okay, this will undergo corrosion. And for other materials, in some environment, maybe if we choose the environment such that out of these steps, if one is stopped, then probably corrosion can be controlled. So, in other environments no corrosion may occur. For example, if we put gold in water, what is happening? Because gold is used in jewelry, okay, and it is a noble metal. So, if we put gold in water, now possibly what happens that no anode half cell reaction is there. So, for gold in water, no anode half cell reaction is there. Okay. So, anode half cell reaction means the like M to M n plus is there, therefore, no corrosion. Okay. That is for gold. That is why it is a noble noble metal. See, you do not see corrosion with gold, but maybe with like silver. Okay, it is not that much that good, like as good as gold. Okay. In the same way, steel will have corrosion. Now, how to measure this corrosion rate, because it is an important thing. That corrosion rate may be measured, can be measured maybe in a very simple way, that you put your substance, I mean the material which is expected material, that is material which is going to be corroded. Okay, you put in the environmental condition. So, keep in environment. Okay, and what you do that you put in the environment, and then you monitor the weight gained or lost, due to weight gained or lost due to corrosion. So, you monitor that. That is the simplest way, like you take a piece of iron, okay, and maybe you keep that iron in the atmosphere. That is a clean piece of iron, and in a clean piece of iron, and then you want, since you want to measure the corrosion rate, you keep in the atmosphere, and for that you measure the weight. That will give you the idea, I mean give you the rate of corrosion, that is change of weight with time. And since it is a slow process, maybe you have to wait for you have to observe for long time. Next is it can be measured electrochemically by constructing cells, and you measure polarization, okay, cathodic and anodic polarization, and application of Tafel and Butler-Volmar equation. You should be able to find out the rate of corrosion and rate of electron transfer in these processes. So, that I already have talked about in electrodic chapter. So, this way, so you can find out the rate of corrosion. That is also a rate process. So, today what we have learned that in this we are about to conclude our session. I mean final conclusion will be drawn in the next lecture, but here we have learned this again we talked about this potential energy surface, and how this potential energy for the reaction, I mean the potential barrier, can depend on the angle of approach, and we have taken the example of H2 plus H reaction. Okay, the more the angle, I mean if it is 180 degree, it is the optimal angle, but if it is less than or greater than, then barrier increases, and that barrier can be overcome with if your reactants have higher energy. So, that barrier can simply be overcome. That is, if the total energy of the reactant is more, then your barrier can simply be overcome. Okay, like this barrier can simply be overcome. Okay, and if cone of acceptance can vary depending on your energy, total energy in the reactants. Okay, and we also have talked about this Polanyi's rule regarding the late barrier and early barrier, and how this vibrational and kinetic energy, vibrational energy and kinetic energy can affect the process. And lastly, we talked about this corrosion process, a very simplistic idea of corrosion. What are the factors, I mean what are the steps that are important in corrosion that we have talked about, and how to control that, and also we have just given you the idea of measuring corrosion rate. Okay, so that's all for today. So in the next lecture, that is probably our final lecture, where we are going to conclude what we have learned in this pieces of lectures. So till then, thank you.